Welcome to the second lecture on DRAMs. So in this lecture, we'll discuss the design space of DRAMs and how we can design them. So of course, a DRAM is a very complex entity, right? So if you thought the cache was complex, well, look at the DRAM. We have a full chapter on it, and we still may be just scratching the surface. So the key question is the first question, and that's an important question. How do the memory controller and the DRAM device communicate? So you could say that, what you do is asynchronous transfer, which means that whenever you have data to send or an address to send, you place it on the bus, and then the DRAM device pretty much picks it off the bus. Sounds easy, but there are many problems. And the problem stems from the fact that the sender and the receiver, so be it the memory controller or the DRAM, they don't share a clock. So as a result, synchronization becomes difficult. So pretty much, look, the idea is something like this, that if you have the bus and you have the receiver could be anybody, could be the DRAM or the memory controller. So what the receiver has to do is whatever bit is coming has to finally enter a flip-flop, right? Let's say it enters a D flip-flop. The D flip-flop is clocked, and what we know is that for something to enter the D flip-flop, it needs to be stable for at least T setup seconds, and then it needs to be stable for at least T hold seconds after the clock edge. So for this entire duration from like this point to this point, the signal has to be stable. Otherwise, it can enter a very unstable regime. Given the fact that every receiver will have its own clock, the signal cannot arrive in this part, right? Or it can't arrive and it can't go away. So in this setup and hold signal, the signal has to be stable, and that is when the signal has to be latched. That is exactly why communication is kind of tough, because you don't want any transitions in this region. Otherwise, what happens is a phenomenon called metastability. Metastability basically means that the input oscillates, right? So basically the input changes, so the output oscillates, and then you never know whether you're latching in a 0 or 1, that you don't know. That's an erroneous situation. Hence what we have is we send the clock along with the data, or let's say some transition along with the data such that the receiver can match the timing, and this timing signal is known as a strobe. And if the data is DQ, the data signal is DQ, then DQS is essentially the strobe signal, and the strobe signal allows the receiver to, in a sense, synchronize its timing with the sender. So this means that the data is latched in at exactly the right point of time, right? So the receiver would know when it is the time to latch the data, and you can say that this strobe can be positive edge triggered, upward edge triggered, or downward edge triggered. It doesn't matter, but whatever is the convention, and the convention has to be agreed to by both the sender and the receiver. The idea is that it conveys the timing, and the timing is needed for proper latching of the data, and this is the only thing that matters insofar as the strobe signal is concerned. Again, there are two kinds of strobe signals. So as I just said, you could have an active high, or you could have active high means when it becomes 1, it is time to latch, and the other could be active low, which is denoted as a DQS with a bar on top, which means when it becomes 0, it is time to latch. So active high, active low, that's again a matter of convention. But insofar as we are concerned right now, what we care about is that the strobe signal conveys the timing. So one thing to know, so it's time to discuss this full duplex and half duplex business. So almost all memory buses, or let's say very large majority of them, are essentially half duplex, which basically means the data either flows this way or data flows the other way, which is this way. So given that we have a one-way transfer, which is either one way or the other way, it also makes a case for sending this strobe signal either this way or that way. So if you look at asynchronous memory, so we would need multiple strobe signals, right, or multiple signals that tell you when data is to be latched in. So we'll have a row address strobe, again active low, a column address strobe, right, again active low, and we will send the address and the data. So the address lines will be called address and the data lines will be called DQ. So the idea is that when this row address strobe is asserted, so asserted means active low, which means it is 1 when it becomes 0. So that is when you expect the receiver to latch the address, which means that you expect that the address bits are sent before this makes a transition to 0, such that when it latches, it will have those bits already on the bus and then it can safely latch on to them. So of course, if there are 64 lines, 64 parallel copper wires, you expect that the signal on all 64, the signals are stable, such that the moment you make a transition, all of these 64 bits can be read out at the same point of time and latched into their flip-flops. That's why before the strobe, the address signal has to be stable. Once the row has been read, then what we would like to do is we would assert the column address strobe, again active low. We expect the column data to be there on the address bus at this point of time. That's simple enough. Once that is done, then what happens is that the data is sent back. So as I said, most of our examples will be a memory read because that is on the critical path. So what has happened is that the device, which is a DRAM device, has activated the row. You have sent the column, so the appropriate column mux demuxes have been activated, right? And then you read the data, you send the data, and then what you do is you deassert the signals RAS and CAS, which means they move back from 0 to 1. So in this case, of course, you know that the moment it is deasserted, the data should be there. So in this case, these become kind of active high signals, and then the data can be read by the memory controller and the transfer is over. So mind you, in this case, even though there is no clock, no shared clock, it is these strobe signals over here, it is their active low behavior here and active high behavior here, which ensures that the row and column are sent, the data is sent back, and the data is read at the memory controller at the right point of time. And this is purely asynchronous, there is no shared clock. Now coming to this, so what you see is that there is a fair amount of time where you're not doing anything. Here you're not doing anything, here you're not doing anything. At this point of time, the address bus, right, is not sending, so address bus send this, but at this point of time, I'm sorry, the address bus is idle. So we can make this process slightly more efficient. So accesses have spatial locality. So once a row, so a row incidentally in the DRAM is called a page. It's not the same as a virtual memory page, but row and page in DRAM are the same, and that's maybe, let's say, 2 kilobits for every array. So that's a fairly big thing, right? Across all the arrays, it's a lot of memory. So once you have activated it, which basically means the values of those cells are in the sense amps and this feedback is there, then the idea is that you just don't want to remove the data from the sense amps, but instead you can make a guess, and the guess would be a fair guess that the next access would basically read from another region of the same row. The next access would again be another region from the same row, so on and so forth. So the idea is that you need not what is called close the row. Close the row would basically mean pre-charge the bit lines back. Again, you need not do that. You can keep the row activated, which means the sense amps retain their values and keep on accessing them, albeit a different set of columns. So for a single array, each column supplies 1 bit, but across the arrays, of course, multiple bits are supplied. The key idea is the same, that we give a row address, we can give the same column address, but as I said, the same row address and same column address for 264 arrays would produce 64 bits. So that is the most important point, that 64 arrays, if you give the same row column address, would produce 64 bits in parallel, which is something that you can read and send back to the memory controller. So the basic idea is the same. We open the row, means activating the row, which basically means enabling the word line transistors and ensuring that the sense amplifiers are properly in sync with the DRAM cells. So the DRAM cells are weak, but the sense amplifiers are strong. So here again, we use the row address strobe to send the row and the column address strobe to essentially send a column. The moment this is received, we have a separate data strobe signal. What happens with the data strobe signal is that this also is an active low signal. So once we send a column, the data is put on the data bus and the data strobe essentially tells the memory controller when to read it. Slightly later, again another column is placed. Again the data for that is read. So of course, so this is basically, if you have 64 bits, you could have a single strobe signal and that could in a sense coordinate the transfer of all 64 bits. But I'm just showing one column or one array, or actually this could be a set of arrays, it doesn't matter. So basically the strobe signal is common. So again the at the next active low point, which is basically this point, the data for this column is read out. Slightly later, again the next column is placed. So note that the column address strobe again makes a transition from 1 to 0, right? So this is one transition active low, this is one transition active low, this is one transition. Again the column address is slightly placed on the bus slightly before such that the values are stable. And then again in due course of time the data is placed and the data is read, again active low, so on and so forth. So what we are doing is we are keeping the row the same. We are just reading out multiple columns. And the advantage of reading out multiple columns in a row is that in any case it is reflecting our accesses which show spatial locality, and a row is quite wide in the DRAM. The reason being that it's quite wide anyway. Plus the fact is that every array pretty much supplies 1 bit per column, right? But if we have a large number of such arrays, let's say 64 such arrays, we get 64 bits. In the next, let's say transfer window, which is, let's say this is 1, this is 2, again we specify one more column, which could be this one. But one column would mean the same column in all the arrays. That's important, right? So this is basically the same column in all the arrays, which is 1 bit per array, which is nothing but 64 bits for 64 arrays, right? So we get 64 bits again, and then again we specify one more column, and it's one array produces 1 bit, 64 arrays produce 64 bits, and we get that, so on and so forth. So this process just continues, and we have column, 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 data, data, data. So the advantage over here is basically that you are assuming spatial locality, which in a sense does exist, right? So the fact is that if you look at it, a DRAM is nothing but a 3D structure, where if this is an array, this is one more array, so on and so forth. Every access cycle, or every time you access, you read only one bit from a given row column pair. And if let's say there are 64 or 128 such arrays, you read 128 or 64 bits in one go. But the fact is that one row is actually one row for every single array, and that's huge. So that's a fair amount of data. So you will see spatial locality. So once you've opened slash activated a row, which basically means you have enabled all the word line transistors and the sense amplifiers have come in sync with the row. So they are now storing the same data. You can just keep the row activated. No need to precharge once again and delete the data in the sense amplifiers. Just keep on accessing different columns, keep on reading out the data. That would be a very efficient process for you and very fast also. All that you need is an additional or extra strobe signal which you will get. So this method is known as EDO or extended data out. This is still asynchronous. Then we have burst extended data out called BEDO or BEDO. So in this case, what happens is, note that there is still some periods of inactivity here, which is idleness, which is something that we don't like. So just remember this diagram and quickly move to this diagram. So kindly note that periods of inactivity are relatively much lower. And also in this case, we don't have a data strobe signal, right? We have not had the requirement for that. The basic insight is as follows, that we typically read a lot of data in one go, and basically what happens is that even though we may read 64 bits in, let's say, one cycle, and we typically have 64 parallel copper wires, but in terms of the overall transfer, it may be 64 bytes, which is basically 8 such individual 64 bit level transfers. So which basically means that if, let's say, I have a starting column, then I need the next, the next, the next. So I already know that. I kind of know that in advance. So what I can do is, again, I can use the same setup, have a column address strobe, provide the column. But what I can then do is that I can also send the data. So I can say that I can kind of send the data for that column and the next one. Pretty much, right? And then what I can do is, so this again can be, the data can be synchronized with the column address strobe. Again, I can send data for another column, which would be that and the next one. So in a sense, if I send column n, I can send the data for n and n plus 1. So this would mean that the prefetch length is kind of 2, because the other one I didn't specify, but I'm inferring from this value. So I kind of specify one address and the subsequent addresses are generated internally. In this case, the prefetch length is equal to 2. And for both the column as well as the data, the same strobe is used, which is the column address strobe. And the reason the word burst comes over here is basically because we are doing this internal calculation or internal computation, and we are basically getting multiple columns of data, which is, let's say, one and the next. So the fact is that this is more efficient, no doubt, than Edo, right? Bedo is more efficient, and I can increase the prefetch length. So then things will get even more efficient. I can make it 8, for instance. So that will make the process of transmission more efficient. But still, asynchronous transmission requires these complicated strobe signals, is quite sensitive to noise. So that is why synchronization is difficult. And essentially the circuits at both the end, at this end and that end, are complex and cumbersome. As a result, even though we have good, we saw, what did we see? We saw regular asynchronous memory, Edo and Bedo. People are, people kind of have come to this conclusion that a synchronous approach may be better where clocks are indeed used. See, we look at synchronous memory. It is easy to design and verify, no doubt, right? You don't need this complex strobe logic, and you don't have to add other kinds of logic. You can do more at the protocol level, no doubt. And furthermore, you can have a complex hierarchical architecture where in principle you can control different banks differently and do a lot just because they're synchronized with a common clock. Now, if you would recall our earlier discussion, we had said that the data bus is fundamentally faster than what? The address command bus, because the address slash command bus, which is essentially a row slash column ID and the commands that are sent, like read, write, etc., these go to kind of all the arrays, but the data bus in a sense does not. It just goes to all the arrays in one row across the ranks. If you would recall this figure, which I can quickly take you back, this one. So as you can see, the address command bus is connected to everything. So it has a massive RC delay or a capacitive loading, because the more you are connected to, the more is the capacitance and the more is the time constant and more is the slowdown. In comparison, the data bus is not connected to many elements, which is why it is not that slow. So now the idea is that the data bus, that is why, is typically run faster at twice the speed of the address command bus. Because it uses twice the speed, this is known as a double data rate, and all such protocols are known as double data rate or DDR protocols. So we'll see DDR 1, 2, 3, 4, right? So now DDR 5 has also come. Along with DDR, of course, you can have QDR, which is quad data rate, but quad data rate is not very common as of today. So double data rate transfer with the clock, right? That is important. With the clock, this is how it is going to look. So we have a clock which we are presuming is triggered at the positive edge. So at all such positive edges, let us use that as the strobe. So the clock is of course shared, right? So every single signal will synchronize with the clock, and the point is that there will be a separate command and address bus, which could be multiplex, but in this case they aren't. So what we do is that we send the row and we send the ACT command or act or activate command, saying that look, activate the row. It's nothing but open the row and let the send SAM synchronize with it. The next cycle, well, we do nothing, we allow the row to get activated. So we send a no op, which basically says don't do anything. Then we have retained the same name. So we send the column and we call the command a CAS, a column address strobe. So this, as you can see, is a pure artificial artifact, right? Absolutely artificial artifact. And here the idea is that while sending data back, we are using a strobe, but we will discuss more about that later. So in this case, what we do is that the strobe, as you can see over here, we are sending it at twice the rate. So just look at this. This is like one full clock cycle, right? So we are sending it at twice the rate, right? For every positive edge, we are sending data. Every negative edge, we are sending data. So this is kind of like a delay, right? So in this case, the prefetch length is kind of 4, because given a column and a column address strobe, what has basically happened is, so this is the command basically. We are reading 4 bits, and then basically after that, as you can see, it is kind of synchronized with this. So after that, we are kind of, so in this case, we have 3 states for this. For the DQS, for the data strobe, we have 3 states. So let's say the default state is X. So then it transition 0 to 1, then 1 to 0, then again 0 to 1, 1 to 0, and again from 0 to X. So basically this is kind of a tri-state bus. So what we are doing is that any transition is a 0110 transition, means data is coming. I mean, you could argue that this could be synced with that, but as I said, we will discuss the need for this later. And then the point is that after data is transferred, we are giving some time, right, kind of for the bus to restabilize and recover. And what we are doing is that after transmitting 2 of these bits, we are sending a column address strobe once again. So for this to take effect, it will take some time. So take effect basically means when you send the command, it is sent, it is buffered on the other side. Then you wait for the existing operation to finish, which is, I mean, just that finishes, and then the column mux, demux are changed. They are kind of, the columns are activated. So that is why we have one idle cycle here for the read process to finish, and then once that has happened, the new set of columns are activated, and again a new data transfer begins. So as I said, in many cases, given the fact that inside the DRAM we have an analog circuit, typically after an operation, which in this case reading 4 bits, it sometimes is necessary to give kind of a fallow period. A fallow period is a period in which nothing happens, and the reason for doing that is sort of to let the voltages stabilize and clocks to resynchronize and so on. And after that, the new command takes effect. So we clearly issued this command, as soon as we could, and then the new transfer takes effect based on the column value specified over here. So this is an example of a clocked transfer with a strobe, where almost everything is coordinated with the clock. The strobe is also coordinated with the clock, and data is transferred at twice the rate. So this is a very basic bare bones DDR protocol, where in a certain sense we have retained the same names as the asynchronous protocol. Of course, in this case they are commands and they are not strobe signals. So the DDR commands, as we see, is act is activate the row, no-op is one idle cycle of the clock, and then cas is activate column and call is the column address. In this case, as you can see, the prefetch length is 4. So let us look at some subtle aspects of the communication between the memory controller over here and the DRAM cell over here. So we have discussed this earlier also at the time of prefetching, that we typically transfer 64 bytes at a time, which is 512 bits, which basically means that even if we send kind of 64 bits in one round, so we need 8 such rounds to transfer the entire cache of 512 bits, right? The entire set of 512 bits. So clearly, we would like to access one rank. We would not like to access multiple ranks for at least a single transfer. And a rank comprises multiple DRAM devices or chips. Each device has multiple banks and each bank has multiple arrays. All of them put together supply all the data in parallel. Of course, it is possible that, let's say, instead of 8, we have 9 banks where one bank is kept for a standby, it is not used. So all of that is possible and the modern protocols do allow. But the key idea is that data is provided in parallel and it is synchronized with the strobe signal. Because we are sending the strobe, which is kind of being used as a clock, this is known as the source synchronous mode of transmission, where source synchronous basically says that you send the data and you also send the clock along with it, such that the receiver can recover the clock and then recover the data. So let's look at this first. While reading, which was the case over here, all the data transitions are synchronized with the strobe signals transitions, as it is the case here. 0 to 1 data transmission, 1 to 0 data transmission, 0 to 1, so on and so forth. However, in the case of writing, the strobe signals transition kind of happens at the middle of the bit. And the reason is that it is easier to recover the clock this way. So recovering the clock is easier if the strobe signal transition is there. And so reading is what? Reading is reading from DRAM. Writing is writing to DRAM. So when you are writing and kind of you're sending a bit, because the DRAM devices are not, as smart as the CPU, they don't have that much of power and processing power particularly. So that is the reason when you receive the strobe, you expect the signal to be stable on the bus and you pick it up from there. So for writing, the timing is slightly different. And clearly we are sending data in half duplex mode. Either we are writing or we are reading, but never both. So small correction is due here. So quad data rate, something that I mentioned in the last slide, is not 100% correct. So in this case, I said that QDR is just DDR with 4 bytes per a single address or command transition. I'm sorry, 4 times the clock rate, but that is not the case. When you use a full duplex bus, which means it allows seamless communication in both directions, that is a QDR memory, right? So this is where I stand corrected. So my correction is a correction on what I said in slide number 33. This is slide 34, which is that if from a half duplex, if I convert it to a full duplex bus, which means communication both sides in parallel, this becomes a QDR memory. So there are multiple DDR generations, DDR 1, 2, 3, 4. Currently DDR 5 is also there, right? But it was not there at the time of writing the book. So the bus clock speeds have just increased from 100 to 200 megahertz, 200 to 400, 400, 1066 to 800 to 2.13 gigahertz. So currently we will discuss DDR4. It is the state of the art insofar as this book is concerned. So it has a very high bus clock speed. The prefetch length, however, has saturated to 8, which is 8 bits, 8 subsequent bits. And the transfer rate, so as I said, the transfer rate means that you are transferring 2 bits per bus clock, right? For a single clock cycle, you are doing 2. So that is why if it is 800 to 2133, this will get multiplied by 2 to 600 to 4266 transfers per second, right? So this is megahertz, this is million transfers per second, MT per S. So then the idea here is that whatever is the bus clock, multiply that into 2, that will give you the transfers per second because of the D in the DDR, the double data rate. Voltages have reduced, and voltages do reduce to make things faster. But of course, you need to have a smaller technology node also. So transistors need to get smaller. So previously the voltage was 2.5, 2.6 volts. It has steadily come down to 1.2. And the maximum size of a DIMM also has steadily increased from 1 GB to 64 gigabytes, which is quite a bit. So memories are getting faster and larger. Why is that the case? Because the feature size, the transistor feature size is reducing. Hence, as you can see, the clock speed is increasing, transfer rate is increasing, the voltage is reducing, which also means that the speed is increasing. And clearly, because the transistors are getting smaller, you can save more data, which means that the size is increasing. Of course, kindly bear in mind that this is the bus clock speed. It is the speed of the clock speed of the bus that is essentially connecting the CPU with its memory controller to the DRAM. All right. So this is what is happening. So the internal speed of a DRAM actually need not be this high. So this is of course the speed of the bus, and the bus speed is high. Let's say the bus speed is 800 megahertz. The internal speed can be much lower. So the internal speed, let's say if it is 400 megahertz. So to compensate, what you need to do is that in one 400 megahertz cycle, you need to generate 2 bits, which means increase the bandwidth, which is kind of 2 bits for every bit that is transmitted, such that effectively for someone seeing it from the outside, we are generating 1 bit in every 800 megahertz clock period, right? And so the idea is that internally you generate more bits and then you transmit them one after the other on the bus. And internally you can afford a lower frequency as long as you are generating more bits such that they can be transferred quickly one after the other. So in this case, the math is 400 megahertz into 2 is equal to 800 megahertz. That's the reason for every 400 megahertz cycle. So every cycle corresponding to 400 megahertz, if I am generating 2 bits, then I can transmit 1 bit in every 800 megahertz cycle. So this is where I kind of compensate by increasing the bandwidth. There is some DDR math which is just exactly the same thing that I said, which is that the bus frequency is 800 megahertz and my internal clock frequency is 200 megahertz. Then what I do is that my internal data rate divided by my bus data rate is 800 by 200. So it is 4x. And then for every bus cycle, right, so this is essentially the ratio. So for every bus cycle, if I am generating, let's say 2 bits, because it is DDR, then what I need to do, what I get is this value of 8, which basically means that for every internal DRAM cycle, I need to generate 8 bits, which is nothing but my prefetch length, because what I do is that I just generate these 8 bits and I send it. If the weight of the processor memory bus is 64 bits and the prefetch length is 8, then clearly the minimum transfer size would be 64 into 8, because once I read, I will then read one after the other. I will read 8 in one go in subsequent consecutive cycles. So it will be 64 into 8, which is 64 bytes. So let me explain this once again. So the idea is that, look, if you are generating X bits internally, so let's say for every internal DRAM clock cycle, I'm generating X bits. Now the point is that if this is my bus frequency, right? So if my bus frequency is 800 megahertz and the internal clock frequency is 200 megahertz. So then effectively what is happening is that I internally need to generate more bits, right? So if I'm generating X bits in 200 megahertz, so effectively if I look at this from 800 megahertz, from the perspective of 800 megahertz, I'm actually generating X by 4 bits per bus clock cycle. This formula is pretty much catching the essence of that, which is basically saying that my internal data rate is high divided by the bus data rate, which has to be of the ratio 800 by 200, right? And then if I multiply that with the number of bits that I'm sending per bus clock cycle, which is 2, so then effectively what I need to do is that in every internal DRAM cycle, I need to generate 8 bits, right? That is what I need to generate, such that what will happen is that all 8 can be transmitted together on the bus after that, which means that my prefetch length or my bus size should be 8, because I clearly know that I need to generate 8 such that I can quickly feed it on the bus. And as far as I am concerned, so in every internal cycle, if let's say this is an internal DRAM cycle, so you know that in this time period you are actually going to have 4 bus clock cycles, all right? And then if you will have 4 bus clock cycles, then so maybe I can draw 4 bus clock cycles here. This is the first clock cycle, this is the second, this is the third, this is the fourth. So I'll have 4 bus clock cycles. So here if I am generating 8 bits in an internal thing, then in the next time that I transmit in the bus, basically, and since I'm going double data rate, I'll send the first bit here, second bit here, third one here, fourth here, fifth here, sixth here, seventh here, and eighth here. So this basically means that I divide the frequencies, multiply it with 2 because of DDR, and every internal cycle I generate 8 such that I can send them in a DDR fashion on the bus for this particular ratio. So hopefully that should be clear. And given the fact that this is clear, so prefetch length is what kind of I commit. I send one column address and then I generate 8. And because I have 64 such parallel lines, the minimum amount of data that I can generate for a single command is 64 into 8, which is 64 bytes. So I hope this is clear. So the last two slides are sort of confusing, but if you kind of go over it and think over it again and again, it should become clearer. And I have tried to explain in different ways. You can always look at the book, but this is the big basic broad idea. So the equation for the transfer rate would thus be quite clear, that 800 megahertz into 2 is 1600 million transfers per second, 2133 into 2 is 4266 transfers per second. So this equation should be clear, and this 2 comes because of the double data rate. So when I say that a technology is DDR3 1600, DDR3 means DDR third generation. 1600 means 1600 million transfers per second, which is this one. So what is the problem with DDR memory, and why do I need something more than DDR? So DDR memories don't scale. So the bus frequency has kind of reached saturation. It's not going to increase beyond it. And also, given the fact that my bus frequency is quite high, I can't place more devices on the bus. That will increase the capacitive loading. So I can't place the I can't place more DIMMs on a channel, right? So there is a limit to the number of DIMMs that can be placed on a channel, because the entire channel will become slow. Also number of devices per DIMM and so on. So this is kind of decreasing, and because DDR is a well accepted standard, we can't change the standard. So a certain attempt was made to re-architect memory such that, still keeping with the DDR standard, we can in a sense attach more devices to a channel and make the memory controller think that it is talking the DDR language, but actually you are implementing the backend in a slightly different way such that you can have more capacity, and this approach was known as fully buffered DIMMs or FB DIMMs. So what is the crux of the idea? The crux of the idea is that we create a new structure called a decoupling buffer or an AMB between the memory controller and the DRAM devices. Alright. So the AMB stands for an advanced memory buffer. So the idea here is that it is sort of like a dummy interface for a rank. So if you think of this, this is like one rank, and so in this case I'm assuming that you have one rank per DIMM. This is also a DIMM, so I'm assuming it's one rank per DIMM. This is the second DIMM and this is the third DIMM. So in general, you would use such kind of a system where, let's say, there would be a limitation. For instance, it may be the case that your technology, given the fact that it's such a high frequency technology, is supporting only one DIMM per memory bus, but you want to attach 3. So what do? So you attach a fully buffered DIMM, an FB DIMM, which essentially has an AMB which talks to the memory controller, and the memory controller then basically there are some small changes, but then the bus architecture is totally different. The reason being that you are kind of splitting the lines. You have southbound bit lanes where data kind of follows south, which is like to the rest of the memory devices, and then you are northbound when any traffic is destined, destined to the memory controller. So the architecture is like this, that the first memory controller is connected to the first AMB, and then the AMBs are connected to each other using these lanes, where a lane carries a single bit. It's a high speed serial bus because it carries a single bit. There is no need for absolute synchronization with other lanes, so we will see that this requirement has been removed in the interest of performance. And furthermore, this technique is quite reliable in the sense, if let's say this lane fails, then there is graceful degradation and the rest of the lanes can take over, or you have additional spare lanes where the functionality of this can be assigned to another lane, right? So there is some kind of resistance to failure, and the role of the AMB basically is it's kind of like implementing a physical channel, right? But it's a smart chip, so it implements the protocol. So its job is that it communicates with all the devices in a DIMM, and it communicates with other AMBs. So one advantage is that previously the buses used to go to every single device in the DIMM, and that had a massive capacitive loading. But the nice thing with the AMB is that it's a charged, it's a powered, it's an active electrical device which is kind of drawing in current and then converting commands and only communicating with the devices in its own DIMM. For other DIMMs, it is just sending a message to the other AMB. So this is also reducing the capacitive loading of any bus structure within the DIMM, which is quite different from what was happening in DDR. But of course, this is a new memory architecture, and in general the memory community has not been very receptive to changes in the fundamental architecture, even though most FBDIMM architectures are quite or try to be quite compatible with DDR, but again it's not fully compatible with DDR, which is why this architecture did not fly, even though it's a great idea. And in this case, kind of theoretically, you can add as many DIMMs as you want, one after the other, of course the fully buffered kind. and then you can have a huge memory capacity which you actually need in servers. Because as I said, the main reason for requiring fully buffered DIMMs is the fact that you have very long data buses and address buses which need to kind of go to every single DRAM bank and array, right? So basically, this requirement is there, and essentially this bus becomes very long and no decoupling is happening. So as a result, basically the length is long, and it has a huge RC delay which makes it quite slow. So the role of the AMB is very simple. So if you see, this is the memory controller, these are the southbound lanes. You have an AMB over here. So its job is to basically pick up data on the southbound lanes. If it is meant for the other DIMMs, it needs to reconstitute the packet, which means that, as I said, there are multiple lanes which are not synchronized with each other. So either you wait for all the data to come, then you kind of create a new packet from all the serial lanes and you send it to the devices in the DIMM, which is basically kind of sending to all the devices within the same DIMM, right? So as I said, if the data is destined to the devices in the same DIMM, you kind of collect the data and you create a packet and you send it. If it is destined for other northbound or southbound AMBs, other DIMMs basically, there is no need to reconstitute the entire packet. Even if there is a delay between the lanes, let that be. You just relay the packets either southwards or northwards. So the idea is again quite simple. If I were to explain once again with a different set of words, that you have these AMBs, they are connected one after the other. So any, let's say, packet that comes southbound, it could either be destined for the current DIMM of which the AMD is a part. Then what you do is you reconstitute the packet and you send it. Or what you do is that you send it to other northbound or other southbound AMBs. So in that case, what happens is that if you do that, then there is no need to wait and reconstitute the packet. A simple relaying is possible. So what are the features of FB DIMMs? Well, scalability, we have discussed this. A very large number of DIMMs can be connected to the same bus. It is high speed. So all the lanes have significantly reduced RC delays, right? The main reason being that you have an AMB, I'm sorry. So you don't have a large copper wire which is snaking through every device, right? Like a large, it's a very long address bus that will snake through every device and get connected to every device. So that is not the case, right? So this vital act of decoupling also increases the speed. Also, the idea is that we don't need that many channels, because in one channel, if we can kind of connect multiple DIMMs, there is no reason to have, let's say, 3 channels per chip. So we can reduce the number of pins that are coming out of a chip. And of course, there is reliability. So if a few lanes develop faults, it's fine. So in terms of high-speed transmission, let's give an example of how this happens. So as I said, this is where this differs from DDR, and so even though the high-level compatibility the designers tried to maintain, there differences quickly cropped up in the implementation, which is again why the acceptability of this protocol was not great. So we typically have 10 bit lanes in the southbound channel and 14 on the northbound channel. And furthermore, on each lane, per DRAM cycle, we transmit 12 bits. And they could comprise, addresses, commands, status bits, error correction, etc. So the key thing is that the capacity of the southbound channel, right? So basically, what happens is that a lane is basically a sequence of a lane is you can think of it as kind of multiple serial buses all bundled into one, Or if you think of it from the point of view of a DRAM cycle, or if you think of it from the point of view of a bus cycle, then of course it's a high speed serial bus. It doesn't matter in any case. Per DRAM cycle, we are transmitting 120 bits on the southbound channel and 168, which is 14 into 12 on the northbound channel, which is per DRAM clock cycle. And as I said, there are two conceptual ways of thinking about it, right? One is in the physical way, which is a high speed serial bus, but then that will be like 1 bit per bus cycle. Or if you think of it conceptually as a DRAM cycle, you can think of them as some sort of a parallel transmission mechanism. So there are three things: resampling, resyncing and reliability. We have discussed these earlier, but let me still recapitulate and refresh the concepts and also put in some more detail into them. So as I said, between multiple lanes, clock skews will develop over time. So the clock skews, if it accumulates, so one idea could be that you just allow them to pass through the AMBs and you kind of maintain the clock skew. But then what would happen is that ultimately the slowest signal would determine when the entire group reaches. Of course, delays may cancel out over the transmission, but in general, the slowest signal may dominate. The other is resync, which is at every AMB we resynchronize the signals and we reconstitute the packet. If it is resynchronized and reconstituted, then the issue that emerges is that the fact that delays may cancel out, we are not allowing that to happen naturally. So we are increasing the latency at each AMB, and that is an issue. And then we have bit lane steering, which is that if this is the reliability angle, that if any lane develops a fault, then traffic can be diverted to other lanes, which is an inherent strength of this system. So of course, resampling and resyncing, there is a trade-off. And the trade-off that is there between resampling and resyncing is basically that we are making the AMB do more work in resyncing, which means every time, if let's say there are multiple signals, they're coming at different rates, wait for all of them to arrive and you buffer them. The other is resampling, which is basically that you just let them go, just pass through, right? So then of course some hybrid of these have to be implemented depending upon how many AMBs are there one after the other on the row. So FB DIMMs, as I said, never took off because even though there was a high level similarity people tried to maintain, but it never, it was actually turned out to be a very different protocol. So what we can get now, even commercially, are RDIMMs or registered DIMMs, where the idea is that you associate a register with a DIMM, right? A register is a set of flip-flops. And for the address and command buses, you kind of buffer them. Instead of having one copper wire that is sneaking through every device, you kind of have a buffered copper wire. This means that you support all the regular DDRX protocols without any modification whatsoever. But it's just that this process of buffering adds a little bit of latency, which to a large extent is tolerable. Absolutely no issues. But the great advantage is that we don't have a large RC delay. The RC delay is kind of kept, it is kept under wraps. It is kept capped. All right. Because the RC delay is capped, or it is kept under wraps, or it is kept under a limit. So what happens is that we can add more devices to a regular channel, as was happening with FB DIMMs. Of course, the resample, resync, reliability and all the other advantages that we are getting from FB DIMMs we will not get. But the advantage is that we can use regular DDR protocols, right? And the only difference is that for many of these, for address and command buses, we are placing buffers because the data buses were anyway fast, but the address and command buses were slow. But the moment we place buffers on them, the RC delay reduces, the latency increases, but we are fine with that. right, to some extent. And then what happens is that, the nice thing with buffers is that even though the latency increases, this latency doesn't hurt us because we can pipeline, right? So it is not, the increasing latency is not a bad thing if you are able to pipeline it, which in this case we can. So what we are basically doing is, instead of one long wire which is snaking through, we are now adding buffers, and we can kind of pipeline these buffers. So the increased latency because of buffering and unbuffering is kind of gone, right? We are not seeing the effect, basically because now we can connect any number of devices, and everything happens in a regulated fashion, right, because of these buffers. And the buffers internally, you can also regulate their transfers. So that is why our DIMMs or registered DIMMs, which are slightly more expensive, are the ones which are used. So now we have discussed the design space of DRAM. So next we will discuss DRAM timing, specifically the DDR4 protocol.